Okay, let's start with the Zendu update. Okay, regarding the seed sidechain withdrawals, as we also seen the last week, this is one of the main tasks that we're working on the mainchain side. Just a little recap of what it is, because we saw a few questions in the past few days, and so maybe it's a good idea to have a little bit of a recap on what is it and why it's so useful. So let's say that if we have a sidechain out there that is working properly, it will continuously provide a certificate within the expected time frame, and everything will be and the withdrawing from that sidechain will be managed by submitting withdrawal requests within that sidechain. But we wanted to have, even a proper way for withdrawing from a sidechain, even if this sidechain was totally maliciously controlled or for whatever reason stops working. So, and we did this to have the users' funds safe in a way that they will be able to withdraw them, even if it is not working anymore, the sidechain. But what is the issue? How mainchain will be able to let a user withdraw from a sidechain that doesn't know how it is done? Because there will be not any more interaction between the user and the sidechain itself, because the sidechain is not working anymore. It's finished. It's not providing any more certificate, and it's done. So, and this process is even more useful if you see it in the context of data availability attacks that are, a kind of attack that can apply to when you're using snarks to provide proof of something, but if the something that provided the proof is not public for any reason, because there was a majority that kept the data private but was able to provide a valid proof, you end up in a situation where the user cannot, provide proof of having coins in that sidechain. But in any case, the seed sidechain withdrawal and the mainchain backward transfer request mechanism are meant to manage even such kind of situations. And so, with the seed sidechain withdrawal, the user will be able to provide a proof. For example, if we are talking about our Latos sidechain implementation, so the user will be able to provide a proof in mainchain that they had some coins in the past and that these coins are still there. And obviously, this will use a snark for providing this proof, and the mainchain will verify that this transaction that is claiming some coins is legitimate. So if it is following the rules of this circuit, and the rules are, I should demonstrate that I had some coins in the past, and these coins remained untouched until now. And this is the way the seed sidechain withdrawal is working, by verifying this proof. Okay, and let's now spend a couple of words about the mainchain backward transfer request, because are related to this. Let's suppose that even you have a totally maliciously controlled sidechain for any reason. So, and you have censorship on obviously the malicious that the 51% will have the possibility to censor request of withdrawing, but we wanted to provide a tool for the user for obliging the sidechain to answer to withdrawal request, main chain backward transfer request. So this is a specific transaction that is posted on the main chain that must be, the sidechain can be designed in a way that the circuit of the sidechain enforce the processing of these requests. And so even if the sidechain is totally maliciously controlled, the circuit can enforce the processing of this request. And if this request is legitimate, can force the malicious actor to add to the next certificate the corresponding withdrawal. So in such a way where even in case the sidechain is totally maliciously controlled, we will be able to provide a tool to the user to withdraw his funds, even if it is not seized and even if it is there, and just censoring the requests on the sidechain side. And this is, for providing even more security to the users. Okay. Now let's go back to the development regarding the sidechain withdrawals, it's about 75% of completion of the development, and the first level of code review is already started in parallel. Obviously, not for the whole.
Alberto, sorry, this is Rolf. I think I finally understand the sidechain withdrawal. Can I just state it kind of the way I think it?
Yeah, sure. Absolutely.
So a person's sidechain private key allows for the creation of a ceased sidechain withdrawal request. So if the sidechain has ceased, and I guess a different discussion would be, there are many ways that we're going to prevent sidechains from stopping. Obviously, there's many ways that we're going to keep sidechains operating. It's only in the ultimate instance that it stops. So your sidechain private key allows you to create a main chain transaction using this sidechain private key to create a withdrawal, even if the sidechain is ceased?
Correct. And we will for sure verify that you are entitled to do this kind of request by, in the circuit, verifying that you have the private key or a valid signature for spending the funds. But moreover, we will also verify in the circuit that there was a previous certificate that committed a state where you can demonstrate that you had these coins, and also verifying that you have left them untouched until now.
And that's the purpose of the creation of all the certificates, to do a summary version of all the various sidechain states. So this also, and you said, so a person's sidechain private key also allows for the creation of a backward transfer request applied to the main chain.
Exactly. I mean, every certificate
I get it now.
Is a sort of a heartbeat where you post a state, a succinct state, and in this succinct state, you can see it as, for example, a Merkle root of UTXOs. And you can, if you know how this Merkle tree is done, you can provide a proof that you have a UTXO in that tree. And there is another structure that is called bit vector that lets you prove that your UTXO remained untouched for all the subsequent epoch until now.
Okay, so that totally makes sense. And I'm sorry to interrupt, but that was the mental block that I had. So when you transfer funds to a sidechain and you're operating on that sidechain, within that sidechain application, you can send it back to the main chain. But if for some reason that sidechain doesn't, the operators of the sidechain don't allow for the transfer back to the main chain, you can, using your private key, create a main chain request to pull your funds back, even if it's ceased or not, because there's been summary certificates all along that are Merkle tree summarizations and ZK snark certificates. So the main chain doesn't have to know the status of the side chain, but by having your sidechain private key, you're able to create this request to the main chain that pulls your funds back from the sidechain.
Correct.
Oh,
That's the idea.
That's brilliant. Thank you.
Thank you, Rolf. Okay, and yes, this is the reason for having the C sidechain withdrawals and the main chain backward transfer request, because we didn't want to rely that everything is working properly. We wanted even to provide a way for the user to retrieve their funds, even if some application is not working properly for any reason. Okay, so this is the way. Okay, let's. Okay, regarding the development of the main chain backward transfer request, we're done implementing all the features required. Complete with the unit test, integration test, and currently we're in the phase of intermediate code review with some minor improvements requested and on the way, ready to be implemented. By this week, we should be able to have it already ready for final review. Okay, let's go on to the other huge area of work that we are currently working on is the proving system. As I told last week, one of the things that we're working on is these sessions where we are detailing the changes that are needed to introduce our new proven system that make, let me say, feasible and performant the recursive proof composition on the sidechain side. The last week we were able to cover the changes that are useful, for example, for speeding up the sum check operation that is involved in many parts during the proving process. And now we're working on detailing the changes that are needed for the introduction of the accumulators for speeding up intermediate proof verification in the circuit, and also the changes, detailing the changes that are needed for getting rid of the inner sum check. So this is something that let me say are the last few things that we are detailing, and then we have all the proving system team members completely aligned on all the next development tasks that are needed to complete the proving system implementation. Okay, and regarding the GPU, we last week we said that we were able to get the Ginger lib integrated with our GPU code, and now we already started adding the CPU improvement as well. And regarding the GPU part, the code had already a first internal code review, and a few small improvements were requested, but are being implemented right now. Regarding the circuits, so let's switch topic and go to the circuits. We were able to define and detail all the circuits that are involved on the sidechain side. Base transaction circuit, the block circuit, the certificate circuit. On the sidechain side, there are many circuits that need to be run. So before proceeding with the development of the circuits, we wanted to have a clear specification of all the, for example, all the public inputs, all the witnesses, all the statement that needed to be checked inside each circuit. So we did this huge work, and we ended up with a detailed specification of all the circuits. And I started reviewing it the last week, and everything's proceeded quite well. And I mean, just a few changes, minor changes were requested, but everything is proceeding well there. And this will be, let me say, a good guide for the developers to proceed on the development, already having a clear specification on all the checks that needs to be done. One of the last thing that I would mention today is the bit vector that is more related to the SDK. And as Rolf, and I was saying to Rolf just a few minutes ago, the bit vector is something that is needed also to prove that a UTXO kept untouched. Even if the sidechain is not working anymore, we have this bit vector. This is a sort of a compressed way for providing the data for the user to provide a proof that his UTXO was kept untouched. And so, but beyond this, we need to create this bit vector, and we have to keep track of it every time you change your UTXO on the sidechain side. And so this is something that we needed to implement, and currently we have implemented the functionality together with some unit tests for it, and we created an implementation that is keeping all together the UTXO Merkle tree, let's call it that way, and the bit vector in a good way. And the first internal code review was already performed, and no changes were requested there. So probably that's all. So thank you, Luca.
Thank you, Alberto.